In this problem statement, we're going to get some practice in incorporating non-ideal interactions and the activity coefficients into our dew point and bubble point calculations. And so in this problem, we're going to focus on a binary mixture that contains equal molar amounts of N-hexane and benzene. So we're going to let this mixture equilibrate such that it forms a liquid phase and a vapor phase. And in the liquid phase, we're going to describe the non-ideal interactions by using the one-parameter Margulies equation, where the A sub naught value, so I'm going to make a little correction here, the A sub naught value is going to be equal to 1089 joules per mole. And so for this mixture, we want to calculate the following properties: the bubble point pressure, the dew pressure at 30 degrees Celsius, and then we want to calculate the bubble temperature and the dew temperature at these corresponding pressures of 760 millimeters of mercury. Okay? All right, and so based on the information in this problem statement, what I want you to do is to pause the video here, and I want you to sketch out a diagram of the system. Okay, so based on the information in this problem statement, we can sketch out a diagram that looks like this, where once again we have this binary mixture of species 1, which is hexane, and species 2, which is benzene, and we're going to let the system equilibrate such that it forms a liquid phase and a vapor phase. And in each phase, we're going to have species 1 and species 2. So X is a liquid phase mole fraction, Y is a vapor phase mole fraction. Okay? All right, and so initially, the system is going to be equal molar. And in the liquid phase, we're going to describe the non-ideal interactions using the excess molar Gibbs energy. And this excess molar Gibbs energy, we're going to use the one-parameter Margulies equation, which is equal to A times x1 times x2, where A is going to be a function of A naught, which is a constant. Okay? All right, and so the way we're going to incorporate the non-idealities into our Raoult's law, or our VLE equilibrium calculations, is going to be through the activity coefficient. And by definition, the activity coefficient is equal to the exponential of the excess partial molar Gibbs energy. And this excess partial molar Gibbs energy, if you remember from chapter 8, is just the partial derivative of the total excess molar Gibbs energy with respect to species I. So T, P, J not equal to I. Okay? All right, so this is how you would take this equation, or this whole thing, plug it into here and take the derivative. But we saw previously in the notes that when dealing with a one-parameter Margulies equation, the activity coefficients end up simplifying to this. Okay? All right, and so with the one-parameter Margulies equation, we want to calculate all these bubble points and dew point calculations. Okay? But before we start with those calculations, one other thing that we need, or that are going to be involved, are the vapor pressures for the hexane and the benzene. Right? So once again, there's different ways to calculate these vapor pressures. One sort of common way that we're going to utilize is just by using the Antoine's equation. Okay? So here, A1 minus B1 T plus C1, where A, B, C are different constants. Okay? And, there are many different sources for where you could find your Antoine's equation constants. One useful source is the NIST online workbook. So if you just Google like hexane Antoine constants, this will likely be one of the first hits. Okay? And so using the NIST website, we could find the constants for hexane, negative 48.784 Kelvin. Okay? And when we use these constants, And this T is also going to be in units of K. If we use these sets of constants, it's going to give us a pressure in units of bar. All right. So when we do our calculations, we just need to make sure that everything is converted correctly. Okay. All right. And so for benzene, to get the vapor pressure, you would follow a similar approach. Okay. All right. So now that we have a way to calculate the vapor pressures, now let's go back and let's focus on calculating all these different bubble and dew points. So we're going to start with part A, where it wants us to calculate the bubble pressure at 30 degrees Celsius. So essentially it wants us to find the pressure. If we go back to this drawing, the pressure at which the first bubble of vapor forms, or essentially if we're at a particular composition, what pressure is going to correspond to that liquid line. Okay, so that's what we want to calculate. All right, so part A, what we want to calculate is the bubble pressure at a temperature of 30 degrees Celsius. 303.15 K. All right, and since we know the temperature, to do this bubble point calculation, we're now going to account for the non-idealities, and so we want to use our gamma 1 here. But to use gamma 1, we need to know what A is. So the first thing we need to do is we need to calculate A at this temperature. So A is going to be A naught divided by RT. So A naught is this. R is this. And T is this. So at 30 degrees Celsius, our A value is 0.432. Right. Now that we have A, we could calculate our activity coefficient, 0.432. We could plug in our mole fraction, which was dealing with this equimolar system. Our mole fraction, x2, is going to be 0.5. Remember, for gamma 1, it's going to be a function of x2. So this is going to be 1 minus 0.5. And we find that gamma 1 can be 1.114. Okay. Similarly, if we plug in for gamma 2, because we're dealing with an equimolar system, it also just ends up being 1.114. If x1 and x2 were different, then gamma 1 and gamma 2 would also be different. All right, now that we have the gammas, we could go to our modified Raoult's law. Okay. So we have that for P1, and for P2 it would be this. Okay. All right. And so if we take a look at these equations, essentially what it's saying is that if we had an ideal solution, gamma would be 1, right? And so our partial pressure would just be x1 times P1 sat. But because we have non-idealities in our system, gamma 1 here, since it's greater than 1, essentially the partial pressure of species 1 is going to be higher than it would be for the ideal solution, right? Because this gamma 1 is going to make this product larger. Same thing for species 2, right? So essentially, in the liquid mixture, the species don't like each other, so they would rather be in the vapor phase than in the liquid phase. And so as a result, the effective pressures, the effective partial pressures in the vapor phase are larger. Okay? All right, and so to be more quantitative, we could carry out this calculation. And so at 30 degrees Celsius, we calculate P1 sat and P2 sat. And so if we go to Dalton's law and we have everything plugged in, we know that x2 is just going to be 1 minus x1, we find that our total pressure is 0.227 bar. And once again, this total pressure is going to correspond to the bubble point pressure, right? Because we're dealing with the liquid phase mole fractions. All right, now that we've calculated our bubble point pressure, the other thing we could do is we could calculate the y value that corresponds to this bubble point. So P1 we know is equal to y1 times P gamma 1 P1 sat. Okay? This P here is going to be our bubble point pressure. And so really the only unknown we have now is y1. So one equation, one unknown. And if we solve for it, we find that y1 is going to be 0.41. Okay? And so, even though the liquid mole fractions were equal to one another, we find that in the vapor phase, we're going to actually have less hexane than benzene. So the vapor phase is going to be hexane poor.